Howdy, everybody. My name is Andy. I'm, as Mohammed mentioned, I manage the CUDA Python ecosystem. So if there's anything to do with Python on GPUs, I'm the guy to yell at. So we just want to introduce the NVIDIA team here. We have Jacob, who'll be doing most of the tutorial today. And if you go to this link here, go ahead and find, it's a GitHub repo, and you can download the notebooks and all the content. We'll also be launching that on Google Colab. So if you haven't ever used Google Colab before, Google Colab and get set up there, and we'll walk you through it later. But it's always good to press I accept all your privacy policies and things like that. And being here in Europe, you have extra warnings that pop up everywhere that we don't have in the US. So get through all that, and then Jacob will lead a lot of that. I'll be wandering around the room, and you can raise your hand, and I'll try to come help you if you have any problems. So one of our goals here is to get everybody on a GPU and running code. So additionally, we have Jeremy Tanner here. Jeremy runs developer marketing for all CUDA Python things. So if you have any questions about, just where to find things, like who in the ecosystem exists, or want us to sponsor your own social or come to other things, Jeremy's the guy here, and he's been in the Python ecosystem. Like all of us have been in the Python ecosystem for a long time. I was going to say years, but I realized that some of us don't have as much gray as others, and we don't want to reveal that. So with that, there's a couple of shout outs we wanted to give. As of today, almost everything in the tutorial is working with Anaconda. So how many people use the Conda package management system? Okay, so it used to be you have to go to Conda Forge, and there's all sorts of pain getting CUDA things involved, but now Anaconda is released on the default channels, all CUDA 12.4, a newer release, and so you should be able to say Conda install CUDA toolkit and Numba CUDA, and it should work. We have a social tomorrow night, and we have Peter Wang, who's the CEO of Anaconda, the chief scientist, chief AI scientist. His role changed. Here we'll be talking about CUDA on Anaconda. So definitely come to the social, meet with us, and kind of let us understand your use case so that we can help craft the tools for you. And just as a poll, how many people in the room have used a GPU for some computation? Okay, pretty much everyone. How many people have used CUDA before? Oh, this is pretty good. And when people use CUDA, how many people have done C++ CUDA? Okay, some. And how many people have done Python, Numba, I guess, and Numba CUDA? How many people? All right, and maybe just shout out other frameworks people are using for CUDA who have been doing CUDA from Python. What are people? What's that? cuDF. Oh, that's a great one. cuGraph. Okay, so we got a Rapids fan over here. Anybody use CUDA Python? CuPy. There's some CuPys. How about? All right. So as we go through it, there's a lot of ways to touch Python. What we're going to touch here is really fundamental CUDA and how do I get my Python functions running on the GPU. But I'll let Jacob go into that. Thank you very much.
Cool. Thanks, Andy. Hi, everyone. As I was introduced already, I'm Jacob. I'm a software engineer in Rapids. Mainly focus on how to run things in interesting places. Usually that means the cloud. Sometimes that means HPCs. Trying to help people take whatever it is they're running, whatever they're working, and scaling that out. But this tutorial is kind of intended to be like the very basics, and it's intended to be like the stuff. So I joined NVIDIA about 5 years ago, and when I joined, I knew nothing about GPUs other than gaming stuff, and that PyTorch, TensorFlow, you just magically turn stuff on. And so I started learning different things. Even though my role, I don't actually have to write deep CUDA code or anything in C++, I still wanted to the things. And this tutorial tried to capture some of the stuff I was learning, like a new NVIDIA. So one thing I want to do at the beginning is just kind of, I have like this little kind of intro slide that I just kind of want to go over. So for those of you that haven't heard of Rapids, we're a group within NVIDIA. We're also an open source community, and we build libraries. They're usually like a C++ CUDA backend with like a nice Python face on it to slot into different places in the PyData ecosystem, right? So if you like pandas, you'll like QDF. If you like scikit-learn, you'll like QML. If you like XGBoost, you'll still like XGBoost because we just work on XGBoost. But like, we try and fit into like the existing ecosystem either by giving you drop-in replacements or by contributing to the upstream libraries themselves to make them CUDA accelerated. But one of our like core goals is to try and help people not worry too much about the nitty-gritty of GPUs, right? It's just I'm going to go and buy an NVIDIA GPU, I'm going to run the exact code I already have, and the thing is going to go faster, right? You're just going to buy accelerated hardware and your code will be accelerated. So towards the end of last year, we released this plugin for pandas called QDF.pandas. And this is part of QDF. You install QDF and you kind of get this plugin. And if you're using pandas, can you put your hand up if you are a pandas user? Okay, that's like everyone. Right, so if you're using pandas and you install QDF, if you are in like a notebook environment or an IPython environment, you can load this plugin with this like load extension. There are other ways to invoke it as well in kind of pure Python world or on the command line. But if you load in this plugin, that's it, right? You just carry on using pandas. Like, you don't have to do anything different. All of your existing code will just continue to work. And this plugin will kind of opportunistically accelerate your code. Whenever there's a situation where it can kind of sub QDF in, which is our kind of CUDA accelerated re-implementation of pandas, if you can swap in QDF, we will. If you can't, or it fails, or your GPU runs out of memory, or something goes wrong, it will just fall back to pandas and carry on kind of normally. So in theory, if you've got some really gnarly code, you'll just run in normal pandas well. But if you're kind of writing standard idiomatic kind of pandas, this plugin should give you some good acceleration. And I don't know, you can go on the NVIDIA website and see lots of lovely graphs that just show like thing that took lots of time now takes not very much time. You just install the plugin. And this is available kind of as standard in environments like Google Colab. So if you're already working somewhere like that, this is just there. You just need to load the extension. Otherwise, you can install this, and as Andy said, this is available now in like the Anaconda defaults channel. You can also just grab this from PyPI. But the goal here is to be this like drop-in replacement. And we've got this in lots of other places as well. So if you use NetworkX, you can use like the cuGraph plugin for NetworkX. If you're a Spark user, you can use Spark Rapids, which will just accelerate your Spark SQL queries. We've got all these different places where you kind of drop in a plugin, an extension, and some NVIDIA hardware, and you just carry on as normal. And that's it, really. That's the end of the tutorial. So thank you all for coming. Yeah, fine. The intent of this tutorial is to highlight that, right? Our goal is to give you drop-in replacements and kind of no-code replacement, no-code change replacements. But like, I find the deeper down stuff interesting, and I'm hoping by kind of giving you all some more fundamentals about what GPU programming is, what that paradigm is like, what it's like to write code in that way, you maybe understand how these libraries are accelerating things and how maybe the code that you've written maps onto GPU accelerated code, and hopefully give you a bit more of like an intuition around what is a good candidate for GPU acceleration, what is a bad candidate for GPU acceleration, that kind of thing. So with that, hopefully you've all kind of started going and getting this open. This is a GitHub repo full of notebooks with links to Google Colab and things. So I'll leave this up for a second more, and I'm going to go and grab a glass of water and bring it up here while you're pulling this open. Then I'll get it open and we'll start running through. Okay, so I'm going to start running through things up here. This is the GitHub repo that I linked to. This is basically just full of notebooks and some data and some, kind of content type stuff. Basically, this is what was in the slides. Now, these have been kind of updated reasonably recently to work with Google Colab, just because that's a really easy place for you to go and get a GPU without kind of too much hassle. The other question I'd like to ask is, how many of you have an NVIDIA GPU in front of you, underneath your hands? Oh, there's some. It's rare. It's usually everybody's here with MacBooks, and it's like, how do I get you an NVIDIA GPU? So Google Colab is the way. If you do have a local GPU and you want to try out some of this stuff, you can install all these libraries with Anaconda. If I just go to rapids.ai, here and you go quick start, there's a bunch of instructions here on how to install Rapids. You can install it with pip, you can install it with Conda. There's like a very basic command here. I'll make this a bit bigger. That was the like high-level Rapids package, right? So if you want to put this in your environments or you want to put this in your kind of places, go ahead and install it this way. But otherwise, we can click these links. Now there's a little bit of jumping around. If I click this first one to open up the kind of Zero notebook, it'll drop you into Google Colab. You probably have to log in with your Google account or something, but you should get to this point where you have a notebook open. And we want to click kind of connect up here, and we want to change the runtime type to a T4 GPU. Right? And we click save. And that should be all we need to do, and probably reconnect. But now I have a T4 in Google Cloud somewhere that will run the cells of this notebook. Now, there's like a bunch of different notebooks in this series as well. So as we come onto other notebooks, I think you only get one GPU as part of the free tier. So when you open the next notebook and you click change the runtime type, it will say, oh, you've already got something open with a GPU, and you have to like close the first one to open the second one. We'll jump through these hurdles together, but just kind of pre-warning you of what's going on. But yeah, in this compute environment, I have a GPU and I have kind of the standard Python libraries that come with my Google Colab environment, which has most of what we need for running through this tutorial. But if there's anything else, we'll kind of install it as we go. Now, at like a high level, I want to talk about kind of what is parallel computing, what is GPU computing. And I appreciate a lot of you put your hands up and said you've touched on this before, but I kind of want to go through some of the fundamentals that are maybe things that you don't necessarily think about when you come at things from a Python side, but you do when you come at it from like a C++ side. And so I kind of want to just fill in some of those gaps to help cover some of that and like talk about the CUDA development model. But then we'll dive into some Python libraries and actually just write some code, very simple code that will run on GPUs. And then we'll start moving up abstractions through to libraries like QDF and CuPy and these higher level libraries before you get all the way to the like full-on plugin level of just I'm going to keep using pandas and I'm just going to use your plugin. Like we're going to start from the kind of the lowest point in Python and work our way out from there. The other things that I kind of want to show you is really understanding, like, how do I poke the GPU in different ways? How do I know what it's doing? How do I know how much memory is being used? How do I know how it's being utilized? Like, how do I debug? How do I get into that? And Andy has like a section that he was going to talk to you about some kind of deeper tools as we go through this. Now, in terms of breaks and things, there are like labs in the tutorial. There'll be like sections where I just kind of leave you to go through a notebook and figure it out. So that's also a good opportunity for breaks. And then appreciate this is like a double tutorial slot. The other tutorials in the other rooms are going to have 2 tutorials in this time slot with a 30-minute break in the middle. So we'll break at the same time everybody else does because I think there's going to be coffee and whatever. So we'll go for an hour and a half until 10:30, then we'll break for half an hour, and then we'll come back and do the second half. So hopefully we'll cover like the fundamentals and low-level stuff in the beginning, and then we'll get on to kind of higher-level libraries and things towards the end. So yeah, there's a bunch of instructions here on running things, but that's it for this notebook. There's not actually anything to run in this notebook, but it's a good opportunity for me to show you. If I come back, I want to leave. If I come back and open the next one, right, second link, opening Google Colab, I'm then going to change my runtime type again to T4 GPU. Click Save, click Connect, and it will complain at me and say, you have too many sessions. So I'm just going to go Manage Sessions, and I'm going to click the little bin next to the first one because I'm done with that. And then I can close and connect, and it should connect this time. So to start at the very high level, let's talk about what is the difference between just a CPU and a GPU and how we execute instructions differently on those different kinds of hardware. Now, this is an image that I picked from the kind of C++ documentation, but it shows a bit of like a high-level overview of what the actual processors look like on the inside. Right, so a CPU has like a handful of cores that execute instructions sequentially. Right, they'll just run through each line of code, each instruction, whatever programming language you're running in, it's going to be doing one thing at a time. It's got some cache, it's got all these different things, but each core is like a discrete thing, and you think about things like processes that the operating system handles, or you think about threads if you want to do some kind of multi-threaded application. But then on the GPU side, you just have way more threads, and you control them kind of as one. So there isn't these abstractions of like processors and threads and things as you would think of on a CPU. You tend to just think of the GPU as this huge block of threads, and I'm going to tell it to do some parallel operation, and it's going to utilize all of those threads kind of in this single function call almost. I'm going to call a function, and it's going to run that on a GPU. Now there's a video that I quite like. Run anyway. There's a video I quite like from the NVIDIA YouTube channel. It's a few years old now. Hopefully it plays nicely on here. The sound doesn't hugely matter, right? But if anybody here is a fan of Mythbusters, NVIDIA got the Mythbusters guys to come and do a demonstration of what the difference is between CPU and GPU computing. So I'm going to skip a little bit through. But first they have this robot. This is the CPU robot. This is basically an arm with a paintball gun on, and it is drawing a picture, right? It's shooting one paintball at a time at a canvas to draw a picture sequentially, right? Now this is their GPU robot. It's slightly larger, but fundamentally it's the same thing, right? It is a paintball gun. It's just really big, it's really opinionated, it's really parallel because they've got all of these different barrels, and they've set the initial conditions of this machine in a certain way. Right, they've loaded each one of these barrels with a specific paintball, and they have kind of one single point of control. So they can come to this machine and they can press go, and then based on the initial conditions that they've set this machine in, it will paint a picture, right? And it's like a single operation. It's a single parallelized operation. It's very different to what the CPU is doing. And yeah, let's let them count down and we'll watch them paint a picture. Hooray. Right. So you can see here, this machine was much faster and much more kind of tuned to doing this job, right? You can imagine with that CPU, with this paintball gun on an arm, you could do a lot more. You could change that paintball gun for something else. It's a bit more versatile, it's a bit more flexible, right? Whereas with the GPU, you've got this like really powerful piece of compute that you can set up in some way and then do big parallel operations on. And so you kind of have to think about this difference in I'm going to set up my state, I'm going to run some execution, and then I'm going to retrieve my state from that kind of processing paradigm. And this is kind of where my interest began, I guess, from like a beginner in this world of like, okay, you have all these threads and you have these parallel operations, but like how different can each thing be, right? If you imagine in this analogy of the paintball gun, they've put a different color paintball into each barrel, right? If you think of each one of these barrels as the threads of the GPU, there's different data kind of corresponding in memory to each one of those threads. And so as the operation begins, something different is going to happen. Now, when we write GPU code, we're doing the same kind of thing, right? We write a function that will be called by all of these threads, but that function will take some data from memory, and each thread will take a different piece of data, and then it can make different decisions, right? You can put if statements in there, you can put whatever in, and you can branch off, and each thread can go off in like wildly different directions if you really want it to, and do very different things. But the challenge there is this parallel execution doesn't finish until the last thread finishes. Right? So when you write this kind of code, you want everything to roughly take the same amount of time. Because if there's one thread kind of straggling on, it's going to bog down everything else. All the other threads are going to be waiting for this one thread that's gone off on your crazy if statement journey through. So we'll come on more into specifics of that in a minute. But the next question I had after this kind of thing is like, okay, I have a machine, it has a GPU in it, I run different programs on that machine and they use the GPU, but how do I, as a developer, write code that then runs on that GPU? And the analogy that I like for this is thinking about, well, if I had my laptop and I had a server somewhere else, how would I run code on that server? Right, well, the first thing I need is my data to be available on that server. I need to kind of push data to it somehow. I need my application to be available on that server, so I need to kind of write some code on my laptop and then push it somewhere. Do I push it into GitHub and then pull it onto that machine? I need to move my code to that machine. And then I need to somehow invoke the code on that machine. I need to SSH to it and run a command, or I need to run Jupyter on that, and then I'm going to prod it through the web interface, or I'm going to use VNC and click some GUI application. There's like lots of different ways that I can connect into a remote machine and kind of interact with it. But the core things is I need my data to be on that machine, I need my code to be on that machine, and then I need to be able to prod that machine. And so in the kind of CUDA ecosystem, CUDA replaces all of these things that you might think about, like SSH and SCP and FTP and GET and whatever. And you have this kind of API that lets you push data from the memory on your computer down onto the memory on the GPU. It lets you push code between the memory, and then it lets you kind of call a function on the GPU and then wait for that function to come back. Now, you can do all of this in C++. You know, CUDA C++ is like a language extension to C++, and you can, you know, CUDA is kind of fundamentally designed around all of this. But I'm not a C++ developer, I'm a Python developer. I'm kind of come from the, you know, I used to work in like weather and climate doing NumPy and Dask and Xarray and that kind of stuff, right? I came from this Python world, like how do I run this code on the GPU? How do I run code that I'm familiar with on the GPU? And so this is kind of where Rapids comes in and where libraries like Number comes in. So for a big chunk of this tutorial now, we're going to talk about the Number library, which is, if you've not come across Number before, it's a just-in-time compiler for Python. And it can work on the CPU, right? So you can write a function, you kind of decorate it with this JIT decorator. And then when you call that function, it will be compiled kind of through the LLVM toolchain into some kind of nice fast code and cached so that every time you call that function, it runs faster. But we also have a CUDA backend in Number. And so there's like a bunch of the CUDA API exposed through Number, which is kind of a nice way to dip your toes in and start playing around with some of this stuff. So I'm going to open up the second notebook and do my little kind of jumping around again of, I should have opened in a new tab. Let me just, okay. Next notebook. So this one is the Number intro. It's always the thing with these tutorials. It's like Colab is a great way to give you all a GPU, but it does depend on the conference Wi-Fi. And I kind of have to just be optimistic about the conference Wi-Fi. There we go. OK, so again, I'm going to go through my little jump of T4, connect, it will complain at me, I'll kill my other thing, and then connect again. OK. Yeah, I just told you to kill that. Anyway, so yeah, Number is this just-in-time compiler for Python. It works nicely with libraries like NumPy, but it allows you to do this kind of GPU programming in Python. And it effectively lets you write Python code that when you call it will be kind of compiled through the like NVIDIA compiler toolchain down to something that can be moved onto the GPU and then executed. And then it exposes all the kind of handles that we need, like moving data around through kind of a nice Python API. And the first thing that we need to talk about is this term that comes up in a lot in GPU computing called a CUDA kernel. Right? And now I found this initially like a very off-putting word, like coming from Python development. Like I know what the Linux kernel is, I know, you know, but what is a CUDA kernel? And so, kind of the way that the Number documentation describes this, and the way I would explain this is, you need to think of a CUDA kernel as a function, right? This is kind of nothing more interesting than a function that I'm going to run on a GPU. And when we talk about developing all these libraries in Rapids, we write kernels for this and kernels for that. Right? These are functions that execute on the GPU. But there's a couple of key differences that make a kernel different to a function. One of them is that a kernel can't return anything. When you execute it, you've got to imagine this kernel is going to be run many, many times in parallel. And kind of wrangling the return output of this is kind of a huge job for the GPU to do. And so it just doesn't, right? You can't return from these functions. Instead, what you must do is you must pass some kind of block of memory into the function, into the kernel, and it should operate and modify that memory in place. It kind of feels weird sometimes from the Python world. I mean, it depends which side you fall into. Some people love in pandas how you have side effects of calling things, and some people hate how you have side effects of calling things. This is a very side effecty pattern, and that's kind of how the world is. So you run your kernel, and you modify memory in place. And then the other thing you need to do is you need to kind of describe to that kernel what we call like the thread hierarchy, which is, again, this is like a slightly gnarly topic to describe. But what we want to describe to this function is how many times it should run, basically. That's the kind of long and short of it. But there are a few different dimensions in which you can describe how many times it should run. So I'm going to spend a bit of time kind of going deep into some terminology here. if you don't follow me through this, it's hard. It took me a few times to get through this as well. But what we think of at a very high level when we call these things is when we run a kernel, we run it in a grid, right? So a grid is just how many times should I run the thing, right? I want to run this function 10,000 times. I want to run this function 1,000,000 times. That is my grid size. It's my overall boundary of like how many times I should run this. But then inside our grid, we have a couple of different dimensions. We have blocks and we have threads. So when we execute, we choose how many blocks we want to run, how many times we want to run a block of threads. And each block is made up by a certain number of threads. And so if you multiply how many blocks you have by how many threads are in each block, that gives you the number of times the function is going to be called. Right, that's your overall grid size. And the reason this happens is because inside the hardware, there are kind of these there's different numbers of cores per GPU for a start. If you buy a T4 or you buy a gaming GPU or you buy an H100 or whatever it is, they've got different numbers of cores. And so this block and thread hierarchy is a way of like batching up the execution of this function basically. And it means that you can run on smaller GPUs or larger GPUs. And the smaller GPUs have fewer threads. They can do fewer batches in one go. It also means that you're not limited to the number of threads that you have. Say you have, 20,000 threads, just to pick a number off the top of my head. If you have 20,000 threads on your GPU, you don't have to call your function 20,000 times. You can call it one time if you really want to be inefficient, or you can call it 10 million times, and it will just get batched through the threads, right? However many times you want this to be executed. But we break this up into blocks and threads so that we can kind of fit that into the different sizes of GPUs. I know this is a bit of like a funky concept to get your head around, and it gets deeper because we start talking about different dimensions as well as we go further into this. So referring back to the number documentation, there's some really nice rules of thumb in here which just says the number of threads in each block should be a multiple of 32. Right? It's great. The first magic number we're going to put in our code is 32. And it recommends that you start with 128 threads per block. You can kind of move up and down. As you add more threads to a block, you're kind of reducing the hardware options you have. Like older GPUs might not be able to run because they might not have that many threads in each multiprocessor and that kind of thing. So the standard rule of thumb of the number documentation is put 128 threads in your block, work out how many times you want to run the function, and then you just kind of use that to work out how many blocks do I need to kind of cover the number of invocations that I want of my function. You can then start tweaking those numbers as you get deeper into this. But we're going to stay up at a high level and just kind of use these rules of thumb to get going. Now, one of the ways I like to describe this in Python is this concept of going from what is a function to what is a kernel. Let's start with a Python function and turn it into a kernel, just to kind of walk through this process of what these differences are. So I have a reasonably simple little piece of code here. Is this big enough for everyone, just before I keep moving? Good, lots of nods, that's fine. Okay, so what I'm starting with here, I'm trying to mimic this kind of environment of a GPU. I'm gonna start with some data. I've just thrown range 10 into a variable called data. I then have a function. This is gonna become my kernel. And then I have a list comprehension. And I like list comprehensions in this case because it kind of feels like running something on a GPU, right? I have this little expression that is like a parallel expression, right? I can run this list comprehension, and I know this is going to happen multiple times. My function is going to be called multiple times, kind of in one line. And that's kind of like a nice mental model to move through. And all we're going to do is we're going to take all of the items in our range, and we're just going to return them immediately. That's just the first thing we're going to do. We have a very simple function. We have a list comprehension, goes through every number in data, and calls foo on that number, and foo just passes it straight back through. Right. Now, the first thing that we need to do to turn this into a kernel is we can't return, right? We can't return I here because kernels can't return. So what we need to do instead is we need to modify memory. So the way we can do this in Python is we can start with our range, and we can also have like an empty output list. And we'll put that in the kind of scope above so the output is available inside our function here. And when we call I'm going to actually run these. Yeah, so you can see, numbers not through 9. Now, if I run this second one, instead of returning each number, we're just going to append it into the list. We're just going to pop this onto the end of the list. And so we're doing basically the same thing, right? We take our input array, we have an output array, and we're going to kind of map our code over this using a list comprehension in this case. And we get the same result out, right? So we're kind of one step towards being a kernel. Now, one challenge that I haven't mentioned yet is we can't have magically changing arrays that get longer and things over time. That's kind of like a Python thing, like dynamic objects like that are not a thing that you would deal with in kind of C++ or GPU programming. So what we actually need to think about is starting with our input data and then making sure that we have a chunk of memory that is already the right size for our output data to go into. So I'm going to import NumPy here, and I'm basically just going to create the same thing again. I've got my range of 10, but I'm just going to make it as a NumPy array this time. And then I'm going to have an output array, and I'm just going to, at the moment, I'm just going to fill it full of zeros and make it the same size as my input array. Right, so I've got like a 10-length array for in and a 10-length array for out. And this time what I'm going to do is I'm just going to assign the position in the output array to the item coming in the input array. And now we can do this just because we've got the numbers 0 through 9, and that kind of maps, the data maps onto the indexes of the array as well here. So when I call my list comprehension this time, one of these function calls is going to get a 0, and it's going to take the 0th element in the output and just kind of put itself in there. One of these calls is going to get a 3. It's going to take the third index in that output array and put a 3 in there. Right? It's just kind of taking something from the input, making some decision about it, and then putting that into the output in some other place. And the idea here is to show that each time this function is called, it's reading from a different bit of memory to all the other invocations, and it's writing to a different bit of memory to all the other invocations. And that's the kind of key thing here is, you can have these functions tread on each other's toes, and so you need to be making sure that when you're writing data back into memory, it's going to be doing it kind of independently, and you're not going to clobber something some other function is doing. So yeah, I run this. I probably ran this already. We get the same array out from there. And that's it, right? This here, it doesn't look like much, my little foo function. But this is a CUDA kernel, right? Because it doesn't return anything. It operates on memory. So the last thing to run this on the GPU is we just need to tell it how many times to run. Now, we're already doing this in our little list comprehension here. But what I'm going to do is I'm going to convert this over to an actual CUDA kernel. And we do this by importing CUDA from number. And then we just decorate our function here with this CUDA.jit. Now, when this gets executed, up until now, we've been kind of taking the input data as our kind of index. We've been this for loop has been giving us the index that we're passing into the function. Now, the equivalent of this in the CUDA world is we have this CUDA.grid function. And this is one of the neat things kind of about GPU programming is each thread within a block, when it's running, can put up its hand and say, who am I? Like within this thread, you've run this function 1,000,000 times. Which one am I? Am I number 5? Am I number 500,000? Like, who am I within this grid? And then it can use that information to make its decision about what memory to operate on and what operation to do. So here I'm just going to say, I want my I, basically. So I'm going to say I equals CUDA.grid, and I want that in 1 dimensions, which we'll come on to in a bit. But we're going to get this index. And now at this point, each one of these invocations knows who it is. It knows what region of memory to read. It knows what region of memory to write. And it's just going to, this is literally just going to copy for something from one array to another. And then the last thing we need to do in order to actually call it is we need to tell the kernel, right? We've got our little kernel here. We need to tell it how many times to actually run, right? I want you to now be executed, and I want you to be executed this way. And the way that we do this in number is we kind of use the square brackets. We kind of overloaded this in Python, but you use the square brackets on the function to pass it in how many blocks it should have, and then how many threads each block should have. So in this case, I'm saying I want 1 block, and that block should have 10 threads, just because that's how many I have. This is like the least efficient way of using a GPU, because there's thousands of cores, and I'm just using like 10 of them, and everything else is going to be idle. But just to try and show you, 1 block, 10 threads. I'm going to pass in our input-output variables. And when I call this function, and we get our output, runtime disconnected, that's sad. Oh, see, that was like an exciting moment, and the technology has let me down. Okay, I'm going to pretend that worked while it is connecting. Right, but this is the point. When I call this function here, foo, square brackets with its configuration, round brackets with its arguments, that will be executed on the GPU. This piece of Python code I've written here is now running on the GPU. And for me, as like a beginner in this world, I was like very excited at this point. It's like, oh, actually, I can write code, like very pure Python that is executed on a GPU and it's executed in parallel. And I kind of understand a little bit more about how to prod this device. And there's a bunch of magic going on here to try and make life easier. Maybe you don't believe me that life is easy at the moment, but there's a bunch of magic here to try and make this process as friendly as possible. Oh, it's connected again. Let's try running it again. Go on, you can do it. Hooray! Okay, I got some warnings because I gave it like a really small thing to do, and it was like, this is silly. Don't do things this small. But you can see the output here is my output array, right? So I took some data in memory and I did some operation on it on the GPU, and that's great. Now we can kind of scale this up a bit from our toy problem to something actually maybe slightly more useful. So let's start with like a bigger array. We'll put 30,000 things in our array. We'll also create an output array. We'll just fill an array with zeros that's the same size as our input array. So we've just got a big array of random numbers, big empty array, and I'm going to write a little kernel that doubles each item in my input array. That's all I'm going to do. I'm going to go through every element in that array. I'm going to take that item out. I'm going to times it by 2, and I'm going to place it back into the output array again. And I'm just going to time this just to see how fast it goes. This is like the pure Python implementation. So I've got my foo kernel here, and just output I equals input I times 2. Right? And then we're going to do it in a list comprehension. And now this is like the worst possible way I could run this code, because, for loops Python, bad idea. But I'm literally just going to loop over every single thing in Python on the CPU. I'm going to double the item, and I'm going to put it into the output array. And it's going to take me 11 seconds in Python. Now let's do the same thing on the GPU. Now I just need to work out this. When we get to this point, we need to start thinking about actually like calculating our threads and blocks, because ultimately in this case, the data is like the deciding factor, right? I've got, how many things? 30 million things. I've got 30 million items in my array, so I want my function to be called 30 million times. Basically, it's like I'm mapping my number of executions onto the shape of the data. And so what I need to do is calculate, like, how does that work? I need 128 threads, because the number documentation tells me that's a good number, 128 threads per block. So I just need to work out how many blocks do I need to kind of cover all of my array. If I imagine I'm kind of windowing over that array, how many blocks do I need to cover that? So I just using a little bit of maths here just to work out, like, how big is the array, divided by the number of threads per block, round it up. Nothing super exciting there, but I'm going to run this now on the GPU. It's exactly the same thing. We've got our foo function, takes input, takes output, first asks, who am I, which element do I operate on, and then it just updates the output element with the input element times by 2. It's the same function as before. And now you can kind of see this expression hopefully reads a little bit better. We've got our function, we can pass blocks and threads, how many times should I run in square brackets, and then input array, output array within our round brackets here. And if I time how long this takes, hopefully it'll be faster than 10 seconds. But I'm also depending on the Wi-Fi. Okay, 300 milliseconds. So that's much, much faster, because I'm getting the GPU to kind of parallelize over this array and operate on this kind of in this kind of vectorized way almost. And that's great. I've accelerated my code here by like orders of magnitude, and that's kind of what our goal is here. Now this is a PyData conference. I'm sure many of you are thinking, why don't you just use NumPy? Like, don't do this with Python for loops. Like, NumPy is a thing. It will make your code go faster. And you're absolutely right here. If I just do the really noddy NumPy thing of going random array times 2 and timing that, that's even faster, right? Because NumPy is very good at this, and it's very idiomatic Python. But the reason that NumPy is faster in this case is because running my code on the GPU, I paid a really big penalty in moving data from the RAM of my machine to the RAM of the GPU, doing my operation, and then moving that data back to the RAM of my machine. Number did this magically for me. As you can see up here, when I call foo, I'm giving it a NumPy array, and I'm giving it an output NumPy array, right? NumPy arrays are on the CPU, they're in RAM. And somehow the GPU operated on these. And so at this point, Number's kind of inspecting and going, oh, you've given me a NumPy array. I can't access that from GPU world, so I'm going to do the memory copying. then I can access it, I'm going to work on it, and then I'm going to just put it back again. And it's kind of helping you out here, but you're also paying a performance penalty because of this helping out that it's doing. Because moving data over the PCI bus is an expensive thing to do. And this is kind of one of the trade-offs you get in GPU world. You have this kind of expensive, this expensive but accelerated piece of hardware, but it's on the end of this piece of string that you have to kind of push things up and down. And so you have to take that into account when you're writing this kind of code. And so to like peel back the covers a little bit more, instead of letting Number do this automatic memory management for us, we can just manage our own memory, and then we can make more sensible decisions. And we can do this by calling, remember we imported CUDA from Number, right? We've got Number CUDA here. We can do toDevice to intentionally push data from CPU memory to GPU memory. So if I just take my NumPy arrays, my random array and my output array, I'm just going to intentionally push those onto the GPU. And I'm going to end up with these two new arrays, right? GPU random array and GPU output array. So this is me kind of explicitly saying, OK, put this over here. I'm going to work on it in a minute. And if I just have a look at it, we can't access the values from our array anymore. They're on the GPU. They're kind of hidden away. You just get this kind of little wrapper that just says, this is a device array. This is an array that's somewhere else. You can have it later. But we can then pass this to our function. We're going to do exactly the same to our kernel. Instead of passing it our NumPy arrays, we're going to pass it our arrays that we've already pushed down onto the GPU. And this time, you should be able to see if Colab wakes up. I am running it like 100 times this time. OK, this took 50 microseconds to do that operation. So we've gone from 10 seconds in Python world down to, what was it, a few hundred milliseconds with automatic memory management, down to tens of milliseconds in NumPy world. But then if we kind of don't worry about the memory management for a second, we're going down to microseconds. So we've got like these keep moving down these kind of order of magnitudes accelerations through the code. So we end up at this point, you can hopefully see here, running this code kind of purely on the GPU is extremely fast, right? And then we have to worry a little bit about memory to try and not be wasteful. Now, the last thing we need to do, our output array that we did here very, very quickly is still on the GPU. I can't touch this. I can't do anything with this. I have to intentionally say, copy this back to the host. Can I have this back now, please, so that I can carry on doing whatever? And it just spits out a NumPy array again. So we're doing our intentional memory copying here. Now, in a situation like this is, these are toy examples, and sometimes it's hard to try and show some of these things because it's kind of obvious, like why would you do this in this case? Because NumPy is just faster, and why would you pay that memory penalty? But this is because this is like a silly small toy example. I'm just calling this function once, and that memory penalty is kind of a bigger proportion of my operation. But if I was running something much larger, much more complex, the memory copy is still the same amount of time. It's still that few hundred milliseconds to copy, a few hundred milliseconds to copy back. But if my calculation in the middle takes like a few hours on the CPU and a few seconds on the GPU, that proportion like completely shifts around. And to kind of show that, if I do something in a really noddy way, I don't think these are actually executable, but if you do this in like a silly way with Number and you leave the automatic memory management on, you might imagine you might write a few kernels that do different operations to that same block of memory. So I start with my input array, I'll call foo on it and get an output array. And then I'm going to call bar, and that will do something else, and then I'm going to call baz, and it will do something else, right? In each one of these cases, I'm copying the data to the GPU, calling the function, copying it back, then copying it back to the GPU, calling the next function, copying it back. And then you're back and forth when you leave the automatic memory management on. Whereas if we swap things around, and at the beginning we say, okay, move everything to the GPU, call kernel 1, kernel 2, kernel 3, now I'm done, I'm going to have the memory back. You're kind of just pushing that memory management out, you're in control of it, and you're kind of paying that penalty. And then ideally, these functions are big things that take reasonable chunks of time that outweigh that memory management. Cool. So that's the end of that notebook. The next one is this Number lab. So we're going to break for kind of 10 minutes, where you can all start working through this lab. Some of you may already be there, but Andy's over there. Jeremy's here. I'm going to wander around, and we can help you with these. That's cool. There's a couple of questions, so go for it. You go first.
For the output array, you push the ones with zeros to the GPU. Don't you just allocate the
Yeah, that was just I don't know, an inefficient thing to do, right? To actually zero out that memory. I didn't need to zero out that memory. I could have just grabbed an empty NumPy array. I've given this tutorial a few times in a few different places, and kind of explaining getting a chunk of zeros felt like people kind of got that. But yeah, you wouldn't actually modify that memory in any way when you allocate it in theory. And there is a call in NumPy to do that, right? You can also in number. Like in this case, I made a load of zeros on the CPU, and then I copied all of those zeros to the GPU. Whereas in NumFOCUS, you can just say, give me a GPU array that's this size, and don't worry about what's in it already. That's like the most efficient way to do it. But sometimes you end up explaining all of that, and it muddies what you're trying to say in the thing. There's another question here.
I didn't get the CUDA grid 1. What exactly were you getting there?
You're getting the ID of the thread within the grid.
Well, why do you actually specify the 1?
So we'll come onto this in the next notebook, but you're basically saying, give me the one-dimensional ID, right? And this is because you can specify the grid in up to 3 dimensions, which helps when you're working with images or volumetric data. But in this case, you just say, okay, I'm going to call this 30 million times. Just treat this as an index from 0 to 30 million. Whereas I could also say, treat this as an index that is like 10 by 3 million, and then give me like my coordinate within that space. But we're just going to say 1 in this case. I kind of wish 1 was like a default argument. Do you know what I mean? That you could just leave it out at this point and just call grid without passing it anything, and it just used 1. But it doesn't. You have to tell it 1, which is kind of annoying.
This is because the grid has blocks, the blocks has threads, so the thread ID is a three-dimensional.
No, it's because you can define everything in multiple dimensions if you choose to. It'll come more clear in the next couple of notebooks. But yeah, so it is 10 to 10 now. Please work through this notebook, and we'll come back together at 10 and go through the solution. Okay, right. Hopefully everybody's had a chance to run through that. I'm going to go through the solution up here. I appreciate that in this notebook it says implement FizzBuzz in CUDA Python, and I apologize if you don't know what FizzBuzz is. I couldn't remember initially when somebody just asked me, because I wrote this notebook a couple of years ago. I'm definitely going to update the intro to this notebook to actually explain. Right, but FizzBuzz is if a number is divisible by 3, it's fizz. If it's divisible by 4, it's buzz. And if it's divisible by 12, it's 4, isn't it?
You can use any numbers you like.
Okay. Yeah, so yeah, I should definitely update this notebook. But the way that, I haven't set my runtime. You can tell at the time that I wrote this, I was doing some like leak code thing or something for some reason, and have now forgotten that knowledge that I gained for that.
Can you turn it up? We can hear you back here.
Yeah. He's just doing it. Thank you. Okay, so we're going to start with some large array like we did before. I'm just going to create a range from 1 to 50 million. We'll do this in NumPy again. And then we're going to create our output array. And again, we could just define an empty array here, but we're just going to create a big zeros-like to get our kind of output memory to put stuff into. We're now going to calculate how many threads and blocks we need. So I've got 50 million elements. I need my function to be called 50 million times. And so I just need to take the shape of my data, divide it by the number of threads that I want in each block, and that will give me how many blocks I need to run over that. So if I calculate that, and then I've got my implementation here, which I've got 4, maybe it's 5, don't know. But anyway, this implementation of code, I'm going to first figure out who am I? Am I the first time this has been called? Am I the 50 millionth time this has been called? I'm then going to pull the item out of the input array that I'm going to operate on, and I'm just going to do some checks to see, am I divisible by 3? Am I divisible by 4? Am I divisible by 12? And then One thing that some people may have noticed is we can't use strings here, right? We can't actually use the words fizzbuzz and fizzbuzz because we can't put strings into memory because the memory has to be of a fixed size and strings don't have a fixed size. So in this situation, we're just going to use numeric values. We're going to use 1, 2, and 3 to represent fizzbuzz and fizzbuzz. And we'll leave all the other things as zeros if they are not one of those options. So this is just a basic assignment. We'll just check if it's divisible by that and then put the number into our output memory. So that defines our function, and then if I calculate this, oh, that's fun. Did I choose the wrong runtime? No. Did anybody else see this? You have to reconnect, okay. Okay, I'm not going to do that because this is like the last one. Then there was an extra credit thing here to just use np.where to figure out the highest fizz. But hopefully this is one of the things I wanted to try and cover in this is to show you how to think about our grid and our data and kind of how they map onto each other. Now I'm going to keep going and we're going to move on to the next example, which is this number Gauss example here. And this hopefully will try and expand a little bit on understanding this kind of thread block grid dimensionality nonsense, basically. So what we're going to do is we're going to start with, oh yeah, I need to set my runtime and connect, and it will complain, and I'll have to kill the other. Oh, maybe I did kill the other. Okay, so what I'm going to do, I'm going to just import matplotlib and a few other things at the top here because we're going to operate on an image. And matplotlib is just a useful library for playing around with NumPy arrays and images. So I'm going to download the number logo, given that we're using the number library. It's a NumFOCUS sponsored project. It has a logo. It's a nice image that we can just play around with. So if I download this PNG, I can just have a look at the type of this. If I do matplotlib's imread, it will give me a NumPy array that represents that image, right? Represents the kind of bitmap of that image. And if I do imshow, we just see the number logo, right, as a matplotlib plot. But okay. And then the last thing I'm going to do is I'm just going to take my image and I'm going to put it on the GPU because we're going to do some operation with it. So I'm going to intentionally say to device, I'm going to put my image on the GPU. I'm also going to create like another image, just empty image, and so that I can operate. I'm basically moving from one to the other. So I just push those down onto the GPU. Now we need to have a look at like the shape of this image, right? We can see kind of up above, it's kind of like long, it's not too tall, and it's in color, right? And that kind of matters here because the shape of this image is 116 pixels high, it's 434 pixels wide, and then it's 4 channels deep, right? Red, green, blue, transparency. This is how PNG encodes the color. And so NumPy gives us this array where we have these different color channels and we have our kind of X and Y. Now, what we want to do in this operation is we want to blur our image. Right, so we want to go over every pixel and we want to apply a blur to it. Now we have our starting input array that looks like this, 116, 100 by 400 by 4, basically. And so our calculation, we want to kind of be the same shape and size. Right? And so what we could do is we could do this in one dimension and say how many actual pixels are there, right? There's 116 times 434 times 4 channels, and that's how many times we want our function to be called. And I could times all of those things together and then call my kernel that many times. And then inside the kernel, I could say, which index am I? And then I could try and unwrap and work out, like, where am I positionally within this image from that index, right? But CUDA kind of helps you out here and also confuses us at the same time by allowing us to kind of specify our grid in that dimensionality so that when we ask for it at runtime, we don't have to do any of this kind of wrapping and unwrapping. So we're still going to use our 128 threads per block rule of thumb that the documentation tells us to use. But we want 3 dimensions here because we've got X, Y, and color channel. And so we're going to basically do a convolution over this image. And so what we're going to say is I want each block to be 2 pixels high, 16 pixels wide, and 4 channels deep. So I can have these kind of almost these little blocks of compute, and they're going to be passed over my image and operate on that. And I've kind of set these numbers intentionally because I know it's 4 channels, so I might as well set that dimension to 4 so that each block is the full depth of the image. This just kind of helps in terms of memory reading, right? And I've kind of kept the proportions the same. So I've gone for 2 by 16 because the image is like 100 by 400. It doesn't hugely matter, but the key thing here is to understand that we have like a shape of our data, and now we're trying to create like a shape of our computation, and that shape should like fit over the top of our data so that we can operate on everything. And so, I don't know, my calculation code has got a little bit more gnarly here. Oh, perhaps if I run on my cells. But I end up, if my threads per block are 2 by 16 by 4, then in order to operate over my whole image, I need 58 blocks by 28 blocks by 1 block to kind of map over my dimensions. And if we multiply these numbers back together just to check, like, what is the shape of the computation that we've calculated here? Because we've got some rounding and stuff going on, we can actually see that the shape of my computation is 116 by 448 by 4. And this is slightly larger than the image. And so this does mean, because my image doesn't fit perfectly into kind of the computational structure of the GPU, there are going to be some extra threads kind of outside the bounds of the image that will still try and do stuff. And so we kind of need to guard for that and be aware of that. Now let's actually write our kernel. So what we're going to do is we're going to write this function called blur. I'm going to cuda.jit decorate it. We have our image in and our output. And now we're going to call cuda.grid3. Right? So this is where we're saying, okay, I've passed you kind of a 3-dimensional index to construct this grid in. And now when you give me back my position inside this grid, I want you to give that back to me in 3 dimensions. And so because we've kind of mapped the shape of our computation onto the shape of our array, we can assume it's a one-to-one mapping where we get these 3 indexes back. So each thread, when it gets to this point, will say, who am I? And it basically goes, right, you're pixel 10 by 4, and you're on the red channel. You should operate in that place. And so this is kind of where you can go. I think you can do 1, 2, and 3 in grid dimensions. If your data is more highly dimensional than that, then you will have to think about wrapping and unwrapping and things. Next thing is we've got this guard here that basically just says, am I inside the bounds of the image? Or am I one of these threads that's kind of fallen off the edge because my block size, my grid size has to be like a round multiple of 32? So you've just got this little if statement. And all that will happen in all of those threads that are outside the bounds, they'll just fail the if statement and finish, right? They'll complete early, everything else will carry on. So we're kind of just guarding this a little bit. Now, what we're going to do is we're going to set the pixel that we represent in our output array, and we're going to read the pixel from the input array, and we're also going to read all of the pixels around it, and then we're just going to calculate the average, right? That's how we calculate this blur. So you just pick up a spot in the middle, you look at all your neighbors, you calculate the average, and then you put that value into the output array. So this is an example of a kernel where some of the threads will read from the same area of memory because they're kind of reading all of their neighbors, and those will be like an overlapping window. But when they write, they only write to kind of one place. It's just their pixel that they're representing. And I tried to lay the code out so you can almost see the little window here. Here's my pixel in the middle, and then you can see the neighbors around it. Now this does kind of one level of blur. It just goes through, calculates this average. We might then want to blur it more deeply, and so I'm just going to go through and I'm just going to do a Python for loop basically to calculate my blur multiple times just to kind of get like a slightly deeper blur. And I did this partly just to kind of talk about that value of copying the data to the GPU and then doing stuff. Right? I've put this data on the GPU. I'm now going to blur 5 times or 100 times or 1,000 times. I don't want that memory like flying back and forth with the automatic memory management. I want this to just stay on the GPU while I completely implement my blur, and then I'm going to get it back later. The other kind of clever thing we can do here is if you imagine I've got my input array and my output array, I'm going to read all my pixels here, I'm going to put them into the output, and I've got my kind of blurred image. And now I want to call this again. So I've got my kind of input array, and I need somewhere to put it. So I'm just going to use the same memory that we used the first time. So I will then blur back into this chunk of memory. And then you can see here, I'm kind of just flipping the pointers around. I'm just going to flip the pointers, and I'm going to blur back to this side, and then I'm going to read, and I'm going to blur back to this side. And I'm just kind of reusing the same arrays each time, rather than reallocating new memory. Now, if I run this, it will blur a few times. And now, if I want to actually plot my image, I can grab that array back to the CPU, and then just use matplotlib to plot it. And so you can see here we have a blurry number logo here. The other things you might notice in this image is along the bottom and along the top and down the sides, there's like a slight gray banding here. And that's because none of this stuff is memory safe. And so when we are if we're at the bottom left corner, if our position is 0, 0, 0, and we read all of our neighbors, we are reading memory outside of the bounds of the array. So we're reading junk from RAM that could be any value, and then we're taking the average of that. And so you end up with kind of this gray smushing along the bottom. So we could also, if we wanted to, we could add some extra checks and say, are my neighbors out of bounds? And if so, ignore those. But I haven't, because I just kind of wanted to demonstrate that you can just read random garbage out of memory if you really want to. So that's that one. Okay, hopefully that's given you a bit more of an insight into kind of this multidimensional indexing. I appreciate it's a bit of a, I don't know, takes you time to get your head around it. Why does it add a new history every time I do that? Leave. So the next one is another lab. It's 10:15 now. Let me just check where we are in the kind of thing. Yeah, so we've got this next lab. I'm going to give you 10 minutes to run through that. It's basically the same notebook again, but instead of calculating a blur, I want you to just grayscale the image. So you have to think about slightly different dimensionality, because each time you operate on an X and Y position, you want to look at all of the channels. Okay, so you don't want to break into 3 dimensions and operate on each channel independently. You only want to break into 2 dimensions and then kind of read across all the channels in order to calculate the grayscale. So have a go at lab 2. It's 10:16 now. I was going to give you 10 minutes for this, but then it's only 5 minutes, and then it's the big main break. So what we'll probably do, if we have 10 minutes now, go through this, and then I'll quickly go over the solution, and then we'll go and have the coffee and big break with everyone. And then when we come back, we can kind of dig into other things like understanding what your GPU is doing, and then looking at higher level libraries.
Welcome back to our second part of our CUDA Python session. Is anyone new? So okay, one person, you've got the content. We did this for you. And just a reminder, I'm Andy. I'll be wandering around. I manage the CUDA Python products line, and so I can answer any questions about CUDA and Python things. Jacob's here. He's on the Rapids team. We're going to dive into a little bit more of the high-level interfaces, maybe get folks how do I use this in my actual daily day-to-day work. And then we have Jeremy here from Dev Marketing. And a reminder, we do have a social tomorrow night with Anaconda and the CTO of Anaconda, or the Chief AI Officer of Anaconda will be here to answer any questions you have. So all those bugs about Portuguese Windows and Anaconda, they're for you, Peter.
Perfect. Okay. Hopefully everybody is more caffeinated now and ready to keep going. So, wrong way. There we go. Right. So this kind of second part of this, chapter 4 and onwards, we're going to start talking about some kind of things that aren't computing on GPUs for a bit, maybe a bit more of understanding what is going on the GPU. How I can understand what it's doing and that kind of stuff. Talk a bit about interoperability, and then we'll go into some higher level libraries that we have within the Rapid suite. So if you're used to using PyTorch or JAX or any of these GPU accelerated libraries, hopefully you kind of get that stuff. And a lot of these things just have a turn on the GPU bit, and then you carry on kind of using those APIs as you would expect. A lot of what we're trying to do in Rapids is either enhance existing libraries or create like an alternative with the same API. So we're going to go over CuPy, which kind of looks and feels like NumPy. We're going to go over cuDF, which looks and feels like pandas. We're going to go over QML, which looks and feels like scikit-learn. But those things are also getting more tightly integrated. But I'm trying to like zoom out here. We've started at the very low level of actually just running functions on a GPU. Now we'll move out to kind of these APIs that we've built out to run GPU things, with that very outer layer being like you don't need to worry too much. You just use the tools that you know and love and just use the plugins. I don't know whether we'll get as far as like multi-GPU Dask stuff in the time, but the materials here, if you want to dig in, I could spend hours and hours nerding out about Dask and distributed computing, but that's mainly because I spend a lot of my time trying to run many GPU workloads. At the moment, I'm trying to run an application on 1,000 GPUs in one go, right? And like that's like a whole nother exciting, interesting world that's kind of beyond the scope of this, but the last chapter kind of touches on that. Now this first notebook here is trying to dig into like what is the GPU actually doing, right? We've written some code, we've run it on the GPU. Now if I was writing some normal CPU code and I was going to run it on my CPU, I would want to know things about like how busy is my CPU, right? How much data is being read from disk? How much memory am I using? All those kind of things. If you're on Windows, you can just open Task Manager. If you're on Linux, you might use Top or some other tool to like get some insight into what is going on, what my utilization's like. And being able to do that, like the GPU has all of these same things, right? It has a percentage of utilization and it has its own memory, and you want to know how much of that's being used. And it has, the GPU can communicate with the CPU over the PCI bus. GPUs can also, if you've got more than one, they can talk to each other over NVLink, or if you've got many machines and you've got a nice InfiniBand like network card, they can talk to each other with RDMA and other fancy things. But like, it's important to be able to understand how do you actually look at this. So one of the things I wanted to show in here is if you're a Jupyter user, we have a Jupyter Lab extension called NV Dashboard, which gives you some like really nice little widgets just to kind of see and understand what's going on. Now this GIF is kind of showing all the bells and whistles and all singing and dancing stuff. But this, can I make that bigger? Yeah. This specific example is loading up NV Dashboard, so it appears when you install it. It appears in the left-hand bar, a little picture of a GPU. There's a few dashboards you can choose from, like memory and utilization. You can see the CPU resources in here as well, but you've also got things like PCI throughput and NVLink throughput and all that kind of stuff. And these open as separate windows within Jupyter Lab with graphs in showing the active usage. And it's Jupyter Lab. You can drag things around and arrange things however you want. So this little example here is just showing on an 8 GPU system, loading up a load of data. I think this is using Dask in this example, but loading up a load of data into the GPUs and doing an operation. You can see this GPU memory filling. You can see the GPU utilization filling. Don't worry about the bottom bars because there's a Dask. But the main thing here is being able to see like how much memory am I using, how hard am I hitting my GPUs. You might write some code and run it, and you see you only got a small amount of GPU utilization, and that's maybe a hint that you're spending a lot of time moving memory around, or you're using the CPU a lot, all these kind of things. This gives you like a really quick kind of glance into that. There are also other tools out there. There's one called NVTop, which is like a command line tool that's very popular. There's another tool called Glances that I end up using a lot, which has got like an NVIDIA extension that you can turn on. So all these kind of things are out there so that you can get a bit of insight into what's going on. But what I also wanted to show you is you can query the GPU directly in Python if you want to. Given that this is like a Python GPU tutorial, let's talk a little bit about the Python API in case you want to grab some metrics yourself, build your own little tool, or build it into something else that you are using to track your metrics. So we can install this library. Let me turn on the right runtime. We have this library which is very helpfully named NVIDIA ML which is not anything to do with machine learning. But this is basically a kind of an interface to something that we have within that NVIDIA driver called NVML. This is like a way of querying the device for information about itself. So we have this library which is NVML Pi. and you import it as PyNVML. I apologize, I'm not in control of this package, otherwise I would have renamed this a long time ago. But you import this PyNVML package and you call in it on it. And these are basically just a wrapper into the C library that you can query the GPU with. But you can do things like saying, how many GPUs do I have in my system, right? NVML device get count. And this is reporting in this Colab environment, I've got 1 GPU. I can query and say, what driver version do I have installed? Kind of all these standard things you might want to learn about the hardware that you've got running. And then you can do things on each individual device. So we need to have a handle for our devices, basically just like a class that wraps up the device. So we're just going to iterate over all of our devices. I know there's only 1 here, but if you're on a multi-GPU system, this would iterate over all your GPUs, get you a handle here, and then you can ask stuff. So you say what is your name? And it will tell you this is a Tesla T4. So whatever cloud you're on or whatever platform you're on, you can find out information about what's on there. And you can ask how much memory has been used. This is in gigabytes. How much memory is free? So you can see this is a 16 gig card. There's nothing really in memory on it. But these are the kind of fundamental building blocks that have been used to build all of these tools, right? So NV Dashboard makes these calls underneath. All of these kind of command line tools make these calls. So I kind of wanted to signal that here, really. I don't know if this is a good time. Do you want to come and talk about Insight stuff now at this point before I dive into Rapids-y things? No. No? Good. Okay. So one of the questions that came up in the break was what kind of profilers and stuff do we have? And there's a lot of tooling that NVIDIA provides. There's a tool called NSYS, which is part of their Insight suite of tools, which is like a full-on profiler that you can see all your different functions getting called, and you can see memory moving back and forth and how much time you're spending on all those kind of things. And this is used heavily by people writing CUDA C++. It will be used by the people writing these libraries that you kind of know and love, right? The PyTorch developers will be using it. Everybody will be using it to get a good understanding of how this GPU code is being written. And if you get deep enough into things, then you may find value in doing that. You can launch a Python process with that, and it will kind of show you all the GPU instrumentation and things. But for this 101 tutorial, I wanted to focus on the very high level. Just, can I see how busy my GPU is? Can I see how much memory my GPU is using? Now, the next thing I wanted to talk about is memory. Now, there was another question that came up before about kind of sharing memory between objects, and can you make use of things like the arrow format? Because in CPU world, it's getting more common to care about not copying memory and trying to be efficient with memory. And can I have a NumPy array that I pass to some other library and it avoids copying it and that kind of thing. So we have exactly the same concept on the GPU. You're always going to be limited by the fact that you have your GPU memory and you have your system memory, and you're going to have to move back and forth on those, unless you're using one of the Grace CPU, GPU hybrid things in a server. You're going to have to worry about those things. But once your data is on the GPU, you still have a whole ecosystem of libraries and tools you might want to use. You might want to use CuPy. You might want to use Number like we've been doing. You might want to use PyTorch. You might want to use whatever it is. And if you're switching from one library to another, the last thing you want to do is have a GPU array in memory, cast it to another type, right? I'm going to go from, Number to PyTorch. The last thing you want to do is copy that to the CPU and then back to the GPU in the other format, right? That's going to be really inefficient. And you don't want to copy from a number array container on the GPU into a PyTorch array. You don't want to duplicate that. What you really want is to just leave that array in memory on the GPU and just kind of dress it up in new clothing and put it into some other tool in some other library. And so we have a few different ways of doing that. The two most common ones are DLPack and the CUDA array interface. Now, DLPack is a way of kind of wrapping up the metadata of that array it's almost like serializing and deserializing the outer layer of that array so that you can pass from one library to another. So if you want to go from, what's highlighted with DLPack? If you want to go from CuPy to PyTorch, you can do to DLPack and from DLPack to cast between those different objects. Or many libraries these days have implemented something called the CUDA array interface. Now, this is something similar to the normal NumPy array interface, but it's like a special method that's implemented on the object. so that when you cast directly from one to the other, you literally just have your array and you just, you do like CuPy.array brackets, whatever your thing is. It will inspect that object and say, do you have a method called CUDA-array interface? And if you do, I'm going to call that, and you're going to tell me all the metadata about the memory and where I can find that array, and I'm going to then convert that into my own type. So suffice to say, if you're using any of these libraries, you can just move back and forth and around. So let me just show you a little bit of that here. This might make me stop my other session. Yeah. Stop. Okay, so I'm going to start out. I'm going to use CuPy. I know we haven't gotten to the CuPy notebook yet, but CuPy is a CUDA implementation of NumPy. It follows the same API as NumPy. If you know NumPy, you already know CuPy. So the first thing I'm going to do is just create a new CuPy array of random data of a certain shape. And this is going to get allocated on the GPU. The memory is going to get populated. CuPy is really nice because it kind of lets you see what's going on. We can see our array here on the GPU. And if I check the type of it, I can do, I can see this is a CuPy ND array. But now say, I want to run a CUDA kernel on this using number, using all the stuff we've written before. I want an array. I've got my CuPy array. I now want this to be in numbers format. In this case, I can just call CUDA.toDevice in the same way that I would pass a NumPy array down onto the GPU. I can just give it this other GPU array, and it'll inspect it and go, oh yeah, okay, I know what that is. That's already there. I don't need to do anything. I'll just put a new Python object around it, and we'll get this number array. So both this, CPR, and this number R are two different Python objects, but they're pointing at the same region of GPU memory. You could do NumPy operations with CuPy. You can do all the number stuff on the number side. And it's working on exactly the same array of data. Or say I want to go to PyTorch, right? I can import Torch, which should be here. And then I can do torch.asTensor, and I can give it the number array. I have to, in this case, intentionally tell it, I want a Torch CUDA tensor, right? Make sure this is on the GPU. But PyTorch will do exactly the same thing. It would just wrap up. It would just look at what I've given it. It will go, oh yeah, I know what this array is. So I now have a PyTorch array that's pointing at the same, a PyTorch tensor that's pointing at the same array. So I now have 3 different Python objects in 3 different libraries, all pointing at the same region of GPU memory. There's been no copying. It's very efficient to do this. And it means I can just kind of swap from one tool to another. Right? If I'm familiar with one and I want some features from another, I can kind of float around between different libraries. You're not kind of locked into any one of these tools. Feel free to experiment. There's a bunch of other libraries that support that. So the next thing we're going to do is talk about CuPy. And again, it's going to make me do the thing. So as I say, CuPy is this kind of low-level implementation of NumPy in CUDA. It's come out of the Chainer project. But it's one of those things so I think when we introduced everyone at the beginning, we talked about the fact that I work on Rapids, right? And Rapids is this suite of tools that are produced by NVIDIA and the community for the Python and PyData and data science ecosystem. But ultimately, we have libraries that are Rapids libraries that we've kind of built from scratch. But there's kind of this broader ecosystem of tools that already exist, and there's no point in us kind of reinventing the wheel or building, we only need to build things that don't exist or things that only NVIDIA can build. But other things in the community, it makes much more sense for us to contribute to those, add kind of developer resource to those, make things more interoperable, and kind of invest in that ecosystem and that community. And CuPy is one of those projects, right? So it's not this isn't something that's come out of the Rapids group, but we consider it part of Rapids because we kind of work on it and contribute to it and care a lot about it. And this is aimed at kind of the NumPy folks in the room. So I'm going to import both of these libraries, NumPy and CuPy. I'm going to do some little funny stuff here. This is partly just to not cheat in my benchmarks. I'm just going to kind of make the GPU stop what it's doing and kind of be ready and waiting. And I might gloss over those a little bit because I don't want to get too bogged down in that. But every time I run some CuPy code, I'm going to call this little synchronize function. And all I'm saying is don't dispatch to CuPy. Actually wait for the thing to finish before you give me back my Python session. Otherwise, the timings will look even more, faster than they really are. So if I create an array with NumPy, I'm just going to time creating a bunch of ones in like a big shape. That took kind of half a second or so to do with NumPy. If I do exactly the same thing on the GPU, this took a much faster amount of time, right? We can use all of these CUDA cores to, I don't know, populate a region of memory with ones, right? But because we're doing this in parallel, we're able to do this much faster. There is like a small penalty in actually dispatching to the GPU and that kind of thing. But you still see like a really nice speed up here. If I'd not called this synchronize, this would have been like really, really fast because Python would have come back before that array had actually finished kind of populating, which is why that's there. But then we can do all of the same kind of stuff you would expect to do in kind of idiomatic NumPy. So if I take my CPU array and I just multiply every element by 5, it is defined, I just defined it. Maybe my kernel restarted. All right, let's try that again. That definitely is the same name, isn't it? Is it because of the timing? There we go, that's better. Okay. Let's just do that again. So I can multiply everything in my array by 5 and see that took a couple hundred milliseconds. You can hopefully imagine that doing this on the GPU is the same kind of operation we've been doing before. Right? We wrote these kernels that will map over, and one of our early examples was multiplying a number. Now CuPy will just do this using exactly the same syntax as NumPy does, right? We can just do my array times equals 5, as I would do in NumPy. And we just see this is much more performant doing this on the GPU. This kind of operation parallelizes really nicely. And this is kind of one of the intents of this tutorial, is we've gone through maybe some pain in the first hour and a half of trying to understand some of these concepts, but now you can maybe see why this is faster, right? Like CuPy is doing all of this hard work for you, but maybe you can see why it's doing this faster. And we can do the same kind of thing. I think this is just to try and show that CuPy is kind of not doing that memory movement back and forth. It kind of knows a bit more about when to actually put stuff back on the CPU, so you can actually see what's going on. That one was like, is it faster? Yeah. Sometimes it's like imports, because I'm like running these things for the first time. There's like a bit of slow stuff going on. Sometimes it's like initializing the CUDA context, and like there's a bunch of like startup penalty that you pay with CUDA applications, which is kind of leaking out a little bit in some of this. But again, like CuPy supports a huge scope of the NumPy API, right? So even doing something like an SVD, we can do that with CuPy in exactly the same way that we would do with NumPy. And it may or may not be faster, but it works, right? The API is exactly the same. Some things work really well on the GPU. Some things will be roughly the same. It depends on the algorithm. It depends on how you can parallelize it. It depends how you can like map over things. But in theory, with a library like CuPy, if you have an existing NumPy code base, you can just import CuPy as NP and crack on, right? And hopefully things will go much faster for you in that case. The other thing we can do is, because we use the array dispatching in NumPy, we can actually use NumPy operations here, and we can just give it a CuPy array. And NumPy internally, when we call any kind of operation like this in NumPy, NumPy will look at what it's been given and say, is this a NumPy array? And if it's not, it will go, oh, who are you? What are you? And it's got some methods that it can inspect on that object and then say, oh, this is a CuPy array. You go and call this thing. I've been told to call this thing. You need to call this thing. So you could, if you want, instead of just importing CuPy as NP, you could import both, and then you just set up your data. You create your data either with one or the other, and then all the rest of your code can use NumPy. You can pass CuPy arrays to NumPy, and it's absolutely fine. NumPy doesn't mind you passing it a CuPy array. It will just dispatch back to CuPy again in those cases. But it allows you to write code that's, write it once and use it with multiple of these. You can also do kind of specific device stuff. Now, I think I wrote this notebook initially on my desktop, which has got 2 GPUs in it. So in this example, you can kind of tell CuPy, I have more than 1 GPU. Please put this array specifically on one of these GPUs. I'm going to choose which one you're going to put it on. So this will probably fail, I think, if I run this, because I've only got one. But if I have more than 1 GPU, that would have put my array on the second GPU. And in PyTorch, there's like a similar concept, right, of choosing which CUDA device you want it on and that kind of thing. So this lets you kind of make those same kind of decisions. So that's kind of an overview of CuPy. There is a lab, so I'm going to give you 10 minutes to run through that. If I just come all the way back up to the top. So there's a CuPy lab here. If you want to open that one up, it's 11:30 now, so we'll go until 11:40, and then I'll run through the solution. As before, put your hand up if you have any questions, and we'll come around and give you a hand with that one. Have a run through the lab solution here. I'll just do my GPU gymnastics. Okay, yeah, Andy just said, just to remind you, every time we open a new notebook and every time we kind of change the runtime and start everything, that's like a completely fresh session. We get like a new VM with a new GPU on, and all the state is kind of lost. It's like restarting your kernel, right? So you have to kind of go back and run through everything again. And if you get partway through, if there's any CPU code and you forget to choose a GPU and you get partway, then you change to a GPU, you need to go and run those first cells again, because it's the same as restarting your notebook kernel. Okay, so we're going to import CuPy. The first thing is to just create a big array with 500 million elements in it. And so we're just going to do an A-range. You may notice with this lab, this is more of like a NumPy test than a CuPy test, but it's mainly, the intent here is to demonstrate that the API is the same. Right? So if we want to calculate how big this array is, we can use n bytes, just like we would in NumPy. If we want to know how many dimensions it has, we can use ndim. If we want to know the size of the array, we can use size. And shape, gives us our kind of vector representation. The next one was to, create 5 million elements representing a linear space. And again, you can just use linspace from the NumPy API. And random arrays. All the random stuff is supported. GPUs are very fast at generating random numbers. They're kind of useful. Any of these kind of things that you can imagine each operation being atomic or independent or orthogonal, whatever phrasing you want to use, GPUs are good at this, right? Because they can do all of these kind of things in parallel. It's where any operation where you have dependencies between the kind of elements and one step needs the input of another step is where you start having to do kind of clever stuff with algorithms to optimize and try and reduce as much as possible. Again, you can sort and reshape and do whatever you like. So CuPy is there to be this drop-in replacement for NumPy. And this is kind of the standard goal of what we're doing in Rapids, really. Just to remind myself, yeah. So one of the questions that came up a second ago, we were talking about graphs down at the front here. If any of you have used the library NetworkX, there's a replacement for NetworkX called cuGraph. But again, that's going down this road of why should we drop in a replacement to NetworkX? Why don't you just keep using NetworkX and we'll do cuGraph in like a plug-in, back-end kind of way? And so that was announced recently that you can now just carry on using NetworkX. And that one is kind of, you get some wild acceleration there because NetworkX is like a pure Python implementation, whereas when you're looking at NumPy and Pandas and things, these are like C libraries, really. And so NetworkX is pure Python. So going from a pure Python implementation of a library to a CUDA wrapped in Python implementation, you're like skipping a step and you get like mad acceleration on that. So if you like graphs, check out NetworkX and cuGraph. Go for it. It's a merge sort. It's a parallel merge sort. Thank you, Andy. So yeah, so there's some benefit. Yeah. Well, it's a different algorithm to the NumPy implementation. Yeah, okay. So I guess these are the situations where the developers have had to make choices about like where do we deviate and where do we not. There's one thing that I didn't mention in this with CuPy is that you can't just cast a CuPy array to a NumPy array. Right? If you do like MP array and give it a CuPy array, it will raise an exception and say, don't do this. This is a really bad idea. And the main reason it does that is because there's loads of libraries all over the place that just randomly call mp.asArray on things. And that's usually just in case you give it a scalar value. And it's like, no, I want an array. I'm just going to wrap it in this quick check to make sure it's this. But in GPU world, that is a move this back to the CPU call. And so you don't want that to happen. And so they made an intentional choice in CuPy to break that. So if you try and do that, it will be sad. And you have to do, like your CuPy array, you have to do like .get, which is a break from the NumPy convention. But it's just it's like an opt-in almost to going back to the GPU. So you may find that might bite you in places. A few years ago, I wrote a plugin for Xarray that allows you to convert the internal structure from NumPy to CuPy, so you can do like GPU acceleration with like Xarray Dask objects. And we had to go through Xarray and like try and tease out a load of the mp.asArray calls and things. Luckily, they were also implementing pint support, so you had unit support in Xarray, and so like we did both things in one go because they had the same problem. So next is QDF. Now this notebook is hopefully a little bit out of date. And I say hopefully because there's been some like exciting stuff going on in the QDF world recently. The goal of this notebook really is to talk through the fact that the Rapids team built QDF, which is a drop-in replacement for pandas. There are like two interesting things that have happened recently is it's installed in Colab by default, so we shouldn't need this install scripty thing anymore. I should just be able to import QDF. Oh, too many sessions. I should be able to just import QDF and it be happy. When it connects. Okay, I'll let it think for a second. The other thing is we have the QDF pandas plugin now. So we generally don't need to use QDF directly. If you don't want to, you can just use pandas directly. And there's another notebook that I will deviate from the tutorial just to kind of show you in a minute after we've run through this. But just to kind of show some differences here, I've imported QDF, which is installed as standard on Colab. I'm also going to import pandas. And I'm going to do a read CSV on with pandas to read some small data frame in pandas, and I'm going to do read CSV with QDF. You can see that operations are the same, the data that comes out of it is the same. And some of these things, some of the things I'm trying to show here is there are different data structures than things we've seen before. Like I think I mentioned earlier, like in the number world, we can't use strings. Like GPUs are traditionally not very good with strings. It's because they need a bit more help and a bit more support in doing that. And now we've kind of moved all the way up the API stack to QDF, which internally uses another library called QStrings. And like all of this kind of support is dropping into place. So we have string support in QDF. We can load kind of any data set here that you would expect to load in pandas. We could do all of our kind of operations on that. But some of this stuff is like, there are gains that you may not expect to get. So read CSV is one place where you get loads and loads of gains because like CSV is not the best format in the world, partly because columns are not typed and you have to do type inference on every value in the data set when you load it. And that's quite an expensive operation. And that's something you can parallelize really well. It's just look at each thing and guess what type it is. You know, ideally, please store your data in Parquet or something more sensible. But we can't choose our data often, and often we end up dealing with CSVs. And so being able to load some data in. And I remember, this might be a couple of years ago now, but I remember we had one customer in Rapids, and like they just had a workload which was read CSV to Parquet. It was like a 2-line thing. And they switched from pandas to QDF, and like they were doing this every day, right? They'd get all this CSV data they were collecting from some system, and they just wanted to store it in some sensible format back into S3 or wherever. And they switched over to doing this on a GPU cluster just purely for data conversion. And we see this come up from time to time. We also had another project where people were using this to load data. It was from like an autonomous vehicles group. And they had some data that had come in from the vehicle, and it was in some format, and they just wanted to kind of convert from one file type to another. They had a slightly more complex thing where they were trying to smush the data around a little bit, almost like transcode it into another format. And so this is a really great operation where operating on individual values like this accelerates really, really nicely on the GPU. Now again, with our QDF data frame, we can do all the normal Panda stuff, right? We have the same dot notation, we have all the same accessors, we can count how many, this is like a Wikipedia data set, I think, so we can count how many pages there are in English, and we can do a group by project, and the project here is the language in this case, to count how many pages. You can do all your kind of standard joins, group bys, like whatever your pandas operations are, you can do in QDF. We have like all this kind of string manipulation stuff, so if you want to go through and convert all of your strings to uppercase, like this kind of thing has been kind of optimized and written to be accelerated on the GPU. The other thing you can do is supply user-defined functions to this, and this works in quite a neat way because before we were writing our kind of custom kernels and kind of obeying all the laws of kernels and not returning and operating in memory and all that kind of thing. But one of the things we can do actually is convert a kind of pure Python function over to a kernel kind of internally. And so if you have an operation you want to do across all the elements in your column or whatever in your data frame, you can write a normal UDF like you would do in pandas and write that in pure Python and do that how you want. And when we call .apply in QDF, it will do some conversion under the hood on this and use number to compile that in exactly the way we were before. It would decorate it with the CUDA.jit or whatever, and you know, it wraps this up in a way so that these returns behave as it should do and everything. But you can basically write pure Python functions, and then you can apply them to a data frame, and that will be just-in-time compiled and accelerated on the GPU without you having to get too deep into any of the, you know, we haven't had to think about threads and blocks and warps and grids and whatever else here. It's just, this is done for you. It will just look at the data frame. It will make some reasonable assumptions. Of course, if you really want to get deep, you could hand-tune these things. These might not be the like most perfect choices of those numbers that we were configuring our arrays with before. Some of the things we were talking about earlier around having 128 threads per block, and when you have multi-dimensions, how do you decide what those dimensions look like? And you might want to look at your data format and how that's stored on disk and then try and choose it. This doesn't do that. This is just giving you kind of the best it can without you having to get deep into any of that kind of stuff. You can just apply your function, and you know, this is like a basic operation that's just if x is less than 5, return 0, it just rounds down, right? But it's just a very basic operation that you can apply over. But we haven't had to do any kind of GPU stuff in this case. We're just using a data frame library. If you've used pandas, you'll know what this library is like. But equally, if you do want to get deeper, if you do want to do some of that tuning, then you can just, you know, import CUDA from number. You can write a custom kernel. This will take the, you know, depending on what you're doing. This is like a for all operation, which is part of the CUDA spec in number. So we create our kernel, and then we have like these other little methods. We haven't touched on this yet, but you can do things like for all in this, and you give it like an array, and it calculates some of these numbers for you. So yeah, the little secret is like all of the stuff we've talked about with blocks and threads and stuff. I put you through some pain that you often don't ever have to think about or do, but I wanted you to go through that just to try and gain some understanding of that well. But in this case, you can just say, okay, I have a kernel, and for all of the things, I want you to apply it. And so we can give it like an input column and an output column, and some kind of value, and these get passed into our kernel, and so we have our input and output column. We have to do the normal kernel behaviors here, right? We have a data in, data out, we can't return, we have to modify memory, we've got this other value, and I just want to reply. We do our boundary guarding and all that kind of stuff. We say, okay, this output column equals the input column times by the multiplier. So if you want to write really kind of deeper or more complex UDFs, you can do that with these CUDA kernels in Python, and then pass them into your data frame to kind of apply across your column. And And you can do the same kind of thing with rolling windows. So maybe you want to calculate like a rolling mean, with a window over your data. You could just define this as like a Python operation here that returns, and then when we do apply, these things get compiled and converted. So all of this stuff goes a lot faster here. Now I'm gonna depend on the conference Wi-Fi for a second. Wish me luck. To just come to this qdf.pandas page. So I'm not actually going to run the cells here, but I want to talk through this one of these notebooks in here. But everything we just did here in this example is we've imported QDF and we're using QDF directly. Right, but the kind of neat thing about this now is we have this qdf.pandas extension, which means that you don't need to import QDF. You can just keep using pandas. So here in this little example that I showed in the opening slides, this is how you would do things in Jupyter. You're doing the load extension magic. But you can also just, it might be in, oh yeah, so there's one way you can do like Python-m QDF pandas and pass it a script that's just pandas. And then there's another thing where you like import something from QDF and instantiate it, but I can't remember where that is in the docs. Anyway, at the very beginning you do one line and you say, turn on QDF pandas, and now here's a load of pandas code, and I've not changed it, I've not done anything, I've not thought about GPUs in any way, I just have existing pandas code. Everybody's got millions of lines of pandas code in their organizations, and this way you can just load this extension, and then you run your normal code. So when you do PD read CSV, it uses the GPU. When you do your group by, it uses the GPU, right? And these work by, like, when you import pandas, we kind of intercept that import and we give you back something else that's not quite pandas, that's kind of wrapping both libraries, both QDF and pandas. And so when you try and do your standard operations, we'll first try and do it in QDF, the fast mode, right? We have like this fast, slow proxy. So we'll try it in the fast mode first, and sometimes that will fail because maybe we haven't implemented it, right? QDF isn't 100% of the Pandas API because the Pandas API is massive and sprawling and unwieldy and changing all the time, right? So QDF is like the kind of core set of the API. But if this proxy here tries to call something that doesn't exist, it will get an exception, and it goes, okay, I'll just do this in pandas, right? So it's got this pandas fallback. So every time you try and do something on the GPU, it has a go. If it fails, it falls back to pandas. And if it falls back to pandas like partway through, and it goes, okay, I've got some GPU memory here, I need to move it to the CPU, and then I can do this in pandas, and then I'll move it back to the GPU so I can try the next step. It's trying to intelligently move things around as things are failing. And also, GPUs have less memory than you generally have on a host system. So if you're, in this example, we've got a T4 on some VM. That T4 has got 16 gig of RAM. Just say, for instance, that VM has got 32 gig of RAM. Like the same data set that I'm working with in pandas might not work on the GPU because I might run out of memory. Right? I might just be working on data that won't fit into the memory of the GPU. In that case, again, it will try, it will fail, it will fall back to pandas. The goal here is that all the existing pandas code will just continue to work and fall back whenever it needs to. But in cases where it can be accelerated and that it kind of works the first time, you should be able to see some really great speed-ups. I can see a couple of questions. I'm going to go over there first, at the back.
So can the user get back any metrics on things are failing in the GPU and in the future, like don't try? It might, as you said, it might be due to memory, it might be due to lack of implementation at the same time, but not trying things that will never work.
Yeah, so the question for the recording is there a way to see what's going on when it's failing, when it's not failing, and understand what's going on? Yes, there's a bunch of profiling tools. I will, maybe it's, I can't remember where they are in the documentation now. There is a notebook that I'm trying to, it used to be linked from this page, and maybe it's moved. I will find it in a minute if I can't find it. Anyway, there we go. Right, so we can do this, qdf.pandas.profile, and then run our code. After the code is executed, we get this kind of nice, rich printout here that shows, okay, these are all the calls that you made to the Pandas API. This is how many times we called it on the GPU. This is how many times we called it on the CPU. This is how long each one took. And you can like dig deeper into like why, what exception was raised, why did you fall back, how can I dig kind of further into that. Yeah, go for it.
When it does the fallback to the CPU, does it copy the data back, or it adds like duplicates?
Yeah, it copies the data back so that it can operate on it. So that, in theory, this will give you an acceleration, right? But if you are in a really unfortunate situation where like every single call fails, the like memory copying and the time spent trying on the GPU may outweigh stuff. But one of the things we've been doing is running the standard Pandas test suite against this with this enabled, and like most of the test suite is passing. So in the like high 90% of the tests are passing and are accelerated, right? And so I think on average we see like a 100x speed up when using this, even in cases where things are failing and things. Got another question?
You mentioned the fact that if your data doesn't fit on the memory of your GPU, that might be a reason to fall back to the CPU as well.
Yep.
I could imagine that if the algorithm itself would be suitable to run on the GPU and then the data is so large that falling back to the CPU will also be too slow, then is it also possible to basically batch your workload onto the GPU?
I mean, you could. It doesn't batch automatically for you, but this is the kind of thing I think where you would dig into the profiler and be like, okay, this is why this is happening. You know, I'm running out of memory, but actually this is a really beneficial. This is a key thing for me to do. I'm going to make a choice to like batch this myself or modify your code. The goal here is to like be a completely drop-in replacement that's not just going to break all of your stuff. Like all of your stuff is intended to still work, and it should still work a lot faster, but we kind of err more on the side of keeping things working rather than trying to be too clever with trying to make things really fast, right? The last thing we'd want to do is say, okay, this thing's really great, it's awesome, you can just drop it in, and 95% of the time your code will still work. Like people are going, oh, well, what about the 5% of the time? Like I can't just drop this in everywhere. So we kind of are more cautious with things like that. But you can then start to tune yourself. And maybe you want to, if you start tuning, maybe you want to actually switch to QDF and use that intentionally rather than kind of like a magic plugin that helps you. Come on, is that a question down there?
When we were showing the image processing in the GPU, it appears some grayscale, so they call it, when using the PDF for time series data frames. Do I need to be careful about something to avoid maybe a kind of data leakage?
So yeah, the question there was in the like low-level stuff we wrote before, we were reading out of bounds memory and doing things we shouldn't be, and does that happen here? As far as I know, this should handle all of that for you. You shouldn't have to worry about those kind of low-level concerns. You should be able to use it as confidently as you use pandas, right, in that sense. Yeah, go on as well.
Just a question back to a mixed code base where it's using various different libraries to do computation, where it's like NumPy, Pandas, X-ray, and all this stuff. Do you have, like, what's the approach to import these libraries? Do you import them all together, or just infers from the part of the simplify stuff? What's the best approach?
Yeah, okay. So the question was if you have a code base that uses multiple different libraries, and we've talked about different ones of those being accelerated, can you use them all together? Should you use them all together? Should you? And I mean, ultimately, some of the ways we've tried, we've talked about implementing these is you should import this GPU library as NP or as whatever, and that might be the way to do it. You might want to try that. In other cases, you might want to have some kind of checking logic. I know in PyTorch it's very common to be like, if CUDA is available, do this, else do that. So you might need to expand on that. In this case, we're intercepting the pandas import. So if your code is using pandas, it's any layer, right? It doesn't have to be you using pandas. If the tool you're using uses pandas internally, that will still get intercepted and will still be tried to accelerate it. But in that situation, like, we're accelerating pandas, so we don't need to, I know pandas uses NumPy internally. We don't need to try and swap out the like NumPy for CuPy because we've already swapped out at that level. So it's a case of experimenting, I think, and figuring out. But if you're talking about something like X-Ray uses pandas, it uses NumPy. And it does all sorts of funky stuff. In that case, I would try the like CuPy plugin for Xarray, which intentionally swaps out the arrays internally. If you try this, I mean, I know they did try to do some Xarray testing, but like Xarray uses objects from pandas like as its own primitives almost, and I don't know how that would behave in this case where you're swapping it out. Maybe you do want the indexes to be on there. Yeah, go for it.
Any benchmarking against pandas 2 window?
Yeah, so yes, we have been benchmarking against pandas 2. It took a little while to get pandas. We didn't like support pandas 2 initially, but it has come out now.
Got some benchmarks there, but I think that's for
Yeah.
other things.
These ones, the pandas 1 benchmark still. I know that I remember seeing a blog post when this came out saying it goes 150 times faster. And I think that's a pandas 1 thing.
It's about 5.
Well, I saw a blog post, again, this is maybe not a thing to quote me on, but I saw a blog post like a week or 2 ago, which is like it's 100 times faster. So I think those are pandas 2 benchmarks, and I wonder if they've reined that number in a little bit because pandas 2 has got some improvements in it over pandas 1. But yeah, you should still see a lot of benefit of pandas 2, and then, pandas 3 is right around the corner, and we'll get on with that as well. Yeah, go for it.
What about the cases when you have non-standard, let's say, types in the data frame, let's say strings, which is usually the problem? Should we even try to use QDF?
So the question is if you have non-standard types. Now, like strings is fine because we support strings. It's when you have like more complex objects or unusual objects in there. I don't know is the honest answer. I would assume it will basically always fall back to the CPU. I think part of the goal here is because it's so easy to turn it on, it's just a case of just try it and see how it runs for you.
Does it work well with type backends?
Does it work well with PyArrow type backends? I mean, yes, it does. So QDF uses like the arrow memory format anyway. All this stuff is like integrated with PyArrow. You've got to remember this is like PyArrow on the GPU, which is different to Arrow on the CPU, because you still have to copy. You can't like reuse that, but we use the same memory format and everything like that. Yeah, go on.
I noticed that there's no space for the Spark in the group by advanced, so I'm curious why that, and also does this work fine with like Spark interviews?
So I don't know why that's not there. I assume the blanks did not finish, but I'm honestly not 100% sure on that one. There's Spark. There is a project called Spark Rapids, which is kind of a plugin for Spark, which uses the low-level. We have a library called libqdf, right, which is the C++ library that QDF is built on top of. We have that like directly integrated into Spark. So if you're a Spark user and you're just using PySpark and you're using Spark SQL or whatever it is to interface with the Spark engine, you can just install this plugin, and at the like lower level, it will use the same primitives that QDF uses. But you don't necessarily want to like put QDF into the Spark stack. We're like going like a level lower of like kind of injecting that into there. But there's like a whole group within Rapids working like purely on Spark stuff and seeing some really great performance of just putting that library in there. Go on at the very back. Yeah, I mean, so the question is, what about polars? In a lot of the benchmarks that we've done, like QDF Pandas outperforms polars in this case.
No, that's not my question. My question is integrating QDF with polars.
Yeah, okay, the question was integrating QDF with polars. The exciting thing about polars is the expressions engine, right? That's the thing. One of the things that makes it like super, super fast is that it does a lot of very clever stuff with optimizing your code before it runs it, right? It defers the execution, it optimizes, it does predicate pushdown and column projection and all that kind of stuff. It would be really nice to have like GPU acceleration Like, there's no reason why you couldn't have GPU acceleration in that space. Do you know what I mean? Because Polars is doing like an optimization and then an execution, and that execution is happening on the CPU, but there's no reason that execution couldn't happen on the GPU. I don't know, maybe future development.
Yeah, I saw that that Rapids and Polars are collaborating to bring this as kind of like a GPU extension of Polars engine.
Yeah, go for it.
It looked to me like your multiple patching pandas when you import it.
Yep.
Kind of sounds like a nightmare to maintain. That's your job. But I'm just curious if you could talk a bit more about how you kind of made that robust and really stressful.
Yeah, okay. So the question is like, we're doing nasty things when you import pandas, and that sounds stressful, basically. Yes. Yes is the short answer. I don't know, a lot of work kind of went into this of kind of how to handle all of these imports. And there's a part inside QDF pandas called the fast slow proxy, which kind of does this like import time patching. Thankfully, I don't have to work on it, but the people that do work on it are much smarter than me, so I'm confident in this. Like, when I first heard about it, I was like, yeah, this sounds gnarly. I think I had like the same reaction, but I think we're at the point now where that has got mature enough where we're like, can we do other things? Are there other things that we could use this same wrapper for? Because they tried to implement it in quite a generic way. So the fact that it happens to wrap pandas and QDF, you could, in theory, wrap two other things with the same API, and it should behave in the same way. So maybe, I don't know, maybe it will become like a separate library at some point for people to build this kind of thing. Yeah, it's all open source. Everything in Rapids is open source. Yeah, I think it's actually in the QDF repo. I think you have to go and dig in the QDF repo. Like I'm sure the object is called like fast slow proxy, because if you like prod at the objects, you see it sometimes. Yeah, go for it.
So we appear to be constrained by memory of GPU. And in the example of going to grayscale, we have to have an input and output memory, and they are exactly the same, but the processing could be done in place. Are there any options to do in-place processing so in and output are the same shared area?
Yeah, so the question is about can we do in-place operations on memory instead of having an input array and an output array? Can we operate in place on that memory? In operations where you can, then I think you can. But in the blur example, you can't do an in-place operation, right? Because you can't. You're reading values that will change, right, as part of the operation. Whereas in the grayscale, like everything's kind of orthogonal, and so you can do that kind of operation. In the grayscale example, we could have just passed one array to it and just modified that array in place. There would have been no issue with doing that. And I think these libraries will do that kind of stuff intelligently for you. Like if you do some kind of operation, like if you just multiply all the things in a column by 2, like it should do that as an in-place operation, I would expect. But I don't know for 100% sure. Go on, everyone, say.
It's related to the cost of copying back and forth between CPU and GPU. So obviously in pandas, because you're doing everything under the hood, the first kind of question is that are you having to copy essentially every time you finish that operation? Or are you kind of holding something in the RAM of the GPU? And then kind of related to that question, how does it grow with the size of the data, that cost of copying? And do you ever get to a point where really can't use that integrated project, and what's the size of the data where you would then have to go to something where you're kind of keeping all the data with multiple kernels that you're going to be working with?
Yeah, okay. So just to repeat that question, it was about copying data, and does this copy the data every time, or does it do any kind of clever optimizations, and like at what sizes do we do we have any kind of rules of thumb or recommendations about what sizes and when you're going to run out of memory? This will only copy data back in the cases where it fails and it needs to do it in pandas, or you try and do something else with the result. You try and convert it to some other kind of object or plot it or whatever it is you're trying to do. At that point where you're trying to access the data, it's smart enough to know like, oh, you're trying to do some like CPU plotting stuff now, I'm going to copy this back. It won't be doing the copying every single time. If you have like a whole chain of pandas operations, it won't be copying back and forth, it will be intelligently leaving the data alone. I mean, none of what we're talking about is like out of core or distributed kind of stuff. So the same rules of thumb for CPU kind of apply here. Like if you have a data set in pandas and you have, you know, whatever it is, 32 gig of RAM, I know a lot of people just work on the rule of thumb that you just want to have like double the memory of whatever your data set is for operations where it does create a copy, or like slightly more than double for those situations. The same applies to the GPU. I think the thing where people fall into like a hole is when you kind of realize that the GPU has a different amount of memory to the CPU, and that can kind of take you by surprise in these cases. I mean, if you have like a laptop with a GPU in it, that's probably a much, you know, the difference in memory is probably very different, right? You might have a 32 gig laptop with a 6 gig GPU or something, right? And it's very different, and you might not get the kind of benefit out of that. If you're running on like a server, you might be, I mean, if you get like whatever the top instance is from AWS, you'll get like 8 H100s, each of which has got like 80 gig of RAM, and then that server's probably got half a terabyte of RAM as well. And so in that case, the amount of RAM in the GPU's total is the same as the amount of RAM on the host, and so you still have to think about multi-GPU stuff a little bit, and if we have time, we might touch on that, but we've only got 15 minutes. But yeah, you're moving your constraint, right, from your system memory down to your GPU memory, and so it's just kind of worth being aware, like how big is my data set and how big is my GPU, and you know, trying to make sure that your GPU has kind of roughly twice the memory of your data set, just like you would in CPU world. Yeah, go on. Sorry, I can't hear, can you? Pickle, as in, can you pickle QDF objects? Honestly, I don't know the answer to that question. I assume these objects can be pickled because in Dask we use Cloud Pickle to move things around. So, you know, I expect we are pickling up these arrays and moving them to different systems and stuff. So, guys, a question about that?
Is anyone looking into streaming data sets into GPU? So let's say you have two data sets merged to get a result, then you send in one more of the same size, or does it have to come back to the CPU?
So the question is, can we stream data into the GPU?
And get around that memory constraint where...
Yeah, so there's a project called QStreams, which is like a streaming data thing. We also have projects like Dask and stuff where you're kind of chunking up your data and you can kind of stream those chunks and do out of core stuff. Like these libraries at their core don't support streaming out of the box, right? It's kind of in the same way that Pandas doesn't, QDF doesn't, in the same way that NumPy doesn't, CuPy doesn't. But as you kind of start getting into, well, how do I solve the streaming problem for NumPy? Like that same solution can be applied to CuPy and that kind of thing. So yeah, Dask or QStreams or other libraries around like that. Cool, okay. This was like an interesting like Q&A detour that I was like not expecting, but it was much appreciated. So that's kind of the end of the like data frame section. I have to click back so many times to get back. Come on, let me get back. Okay, we have a QML example in here, and we also have like a multi-GPU with Dask example. We've got like 10 minutes left of the session, so maybe I should let you choose. Hands up, who wants to go through the QML one? Okay, and then hands up, who wants to go through the Dask one? Oh, more Dask, okay, that's good. Okay, so to just briefly touch on QML, it's scikit-learn, but fast. It's the same idea though, right? It's the same API. You can import QML as, you know, SK or whatever and do whatever you like to do. So when you start reaching the limits of your GPU and you want to go further, or you have data that doesn't fit into memory or things, you need some kind of solution for doing out-of-core operations if you're running out of memory, or you need some way of using multiple systems. Who here has used Dask in like normal CPU world? Okay, so some. So Dask is, yeah, for those of you that didn't put your hand up there, Dask is a library that lets you kind of write Python code that can be distributed, right? And so we have a few different APIs laid down in Dask, which you can write functions. Those functions build up a graph, and that graph can be executed by some kind of scheduler. We run this on a laptop. If you've got more than one core in your laptop and you want to really use all of them in Python, Dask will use all the cores in your laptop. If you've got an HPC with thousands of cores, you can run Dask on there as well, right? And the graph will just be executed by workers on this kind of larger system. And now, Dask is really nice because it has this low-level API, but then it has this high-level API where it implements the Pandas API, it implements the NumPy API. We've got like integration with scikit-learn. It's well integrated into projects like XGBoost. And the goal is the same of like everything we've talked about here. Is like Dask array is intended to be a drop-in replacement for NumPy. Dask data frame is intended to be a drop-in replacement for Pandas. And all it does is every time you call an operation, like mean or whatever, it has like a distributed implementation of that operation that internally has, you know, NumPy arrays or whatever, but it will kind of do like a reduction or whatever in Dask. Now, because we're in this nice situation where Dask wraps, so let's keep talking about Pandas, right? Dask wraps Pandas to do distributed data frame operations. I want to have lots of machines and I want to run some large data frame in memory and do stuff with Dask. And because cuDF implements the Pandas API, we can just do Dask cuDF, right? Dask just wants to wrap a thing that looks like Pandas. cuDF looks like Pandas. We can switch them over. Now, in order to, I'm trying to think where to go with this. Like, in order to run all of these things, we need to actually start the Dask kind of cluster. And there's like a bunch of different ways of doing this. So like most standard way of doing this in Dask is that you just don't think about it. You just create a Dask client, and it magically looks at your laptop and goes, how many cores have you got? Okay, I'll start one worker for each core, and then I'll execute your code on that. But then when you want to move to other systems, we have all these kind of cluster managers that are like little classes that let you create, you know, you can either intentionally create the local cluster, which is what happens internally, where it uses your single machine. You can use SSH cluster, which will just SSH into other machines. It assumes that Python is in the same place on all those machines and has the same environment, but it will SSH into machines. It will create a Dask cluster. You can submit onto HPC. You can run on Kubernetes. You can run on the cloud. There's like paid services that you can use to like spin up Dask clusters for you. And all of this is generally based on the premise of using the CPUs in those machines. It will kind of auto-detect and create workers for those CPUs. So we have another library as part of Rapids called Dask CUDA. And this kind of wraps some of those things, and it just changes the startup so that instead of looking at the number of CPUs, it looks at the number of GPUs. So if you do like local CUDA cluster, this behaves the same as local cluster, except it will just grab all of the GPUs in your machine, start one Dask worker per GPU. And so if I do that in here, which might not actually work on Colab because I skipped an install step, but I'm not going to make you watch this install for 10 minutes. Yeah, I didn't like that. Okay, so when I call local CUDA cluster, it will look at this machine, it will go, okay, there's one GPU, I'm going to start one GPU worker. On my desktop at home, it will say, oh, there's 2 GPUs, I'm going to start 2 GPU workers. If I log into servers, I'll have more or whatever. And I create this client, and this is kind of you know, this is what is telling my Python session that you should use Dask in these arrays. Now let's talk about the like high-level collections a bit here. We have, when you install cuDF, you also get this library called Dask cuDF, which is kind of wrappers for cuDF to make them play nicely with Dask. This isn't the nicest example here, actually. But you can do like Dask cuDF dot read CSV, or kind of any standard pandas operation, and it will load in a Dask data frame, but each partition in that data frame will be a cuDF data frame instead of a pandas data frame. Right? But Dask is kind of chunking this out. It does it automatically if you don't give it any information. If you just have a really big CSV file, it will choose where the partitions are. if you're reading Parquet, it will use the partitioning already in the file format. You can repartition and do whatever. You can tell it how big the partition should be, that kind of stuff. But then you can do all of the like normal operations you would do in pandas, and Dask will first kind of build a graph that represents that operation, and it will pass that to the scheduler. The scheduler will distribute that to the workers. The workers will start executing all of the tasks to do that operation. But inside each of those tasks, it will use the GPU flavor of the library instead of the CPU flavor of the library. And so we can do very large operations. And then beyond that, you then start thinking into, well, how do I communicate between all of these operations, right? If I need to share results between stages in this graph, or if I need to communicate, I've got this very, very fast computation, but I'm still kind of limited by going through the CPU for communication. I'm using TCP, it's using the network stack in the operating system. I'm like pickling things and passing them to the CPU, then maybe to a different machine in the cluster, and back onto the GPU and doing the next thing. So we have a whole load of like accelerated communication within here as well. One of those is a thing called UCX. So you can turn on UCX in Dask, which you just say to Dask, use this instead of the normal TCP communication. And UCX is like a unified communication protocol, and it allows you to use kind of fancy networking hardware if you have any. So if you have GPUs together in a server and they've got like an NVLink connection, which is used for doing really fast direct GPU to GPU memory transfers, Dask will use that in that case. If you're trying to talk from an array, a data frame on one GPU in one machine to another GPU in another system, and you have like InfiniBand, and you can do RDMA and kind of, things that are maybe more common in the HPC world of like, I've got really fast networking and I can do direct memory transfer between machines. It will use RDMA and InfiniBand to transfer from the GPU memory of one system to another system to kind of ease that communication. And then if those things aren't there, it will just use TCP, right? It falls all the way back to doing that. So Dask is trying to break up these operations into small chunks, distribute those across machines, and then try and take out some of the burden of communicating and coordinating across that. The last thing that's maybe worth mentioning here as well is you may want to intentionally run things on GPUs and intentionally run things on CPUs. You may start a Dask cluster which has got GPU workers and CPU workers. One common case that we see for this is, say your data is stored in S3, like trying to read a single chunk from S3 is like not as fast as reading from local storage or something like that. And so the way that S3 scales and gives you really great performance is you make lots and lots of connections to S3, your data's chunked, you read in lots and lots of chunks at the same time. And in these situations, you might have hundreds or thousands of CPU cores in your cluster, and you may have like tens of GPUs. And ideally, you want all the CPU cores to do that read, because you want lots and lots of connections to S3 to saturate all of that bandwidth, pull all that data in, and then kind of condense that down onto the GPU, and then use the GPUs for the compute, because those GPUs are going to be much faster than the CPUs for whatever operation it is that you're doing. So you might spin up like a heterogeneous cluster where you've got CPU workers and GPU workers, you use some for I/O, you use some for computation. Or maybe sometimes you just see situations where you have a big CPU cluster in Dask, but there's one step that would benefit from GPU. You just want we see this sometimes as well with memory. It's like, there's one step in my computation where memory, it uses like 10 times the memory of everything else. So I just want one really big worker that will have lots of memory. Or I want one really big GPU worker that will just do this. And so you can deploy your clusters kind of however you like using the tooling. And then you can use these annotations in Dask. So you can say, run this function, that will run wherever it feels like running. And then here, intentionally, we're saying, everything inside this context manager needs a GPU. We're like annotating it with GPU. And then the next thing we run, that will only be constrained to the GPU nodes. And you can do all of that kind of stuff, so you can build out like complex workflows if you want to with Dask. But this kind of allows you to break beyond the memory limits of your machine. So even if you just want to use if you can use Dask QDF if your data set is larger than memory, it's kind of what we were talking about before. If you want to actually batch through and chunk through, you wouldn't use QDF and you wouldn't use the like Pandas plugin. You would use Dask QDF so that it can do the chunking and the batching. But the goal is still that the API, the Pandas API is roughly the same. Dask has a few things you have to think about when to compute and persist and that kind of stuff. But again, once you've got to that point, you can then think about, well, what if I had more machines? Can this go faster if I scale out, as well as kind of trying to leverage the resource I've got or stream through memory there. Now, we're basically on time, so thank you all for listening. I appreciate this has been like a very long tutorial, and we've gone very deep in some areas, and we've gone very broad in other areas. I really hope you all kind of got something from this. Us NVIDIA folks will be around through the weekend, so please come and ask questions. Like Andy said, there's the social. But if you want to come and talk to us about your use cases or ask more questions, we're just around for the week. But thank you all for your attention, and please enjoy lunch.